So welcome to this third and final video on the local well-posedness of nonlinear Schrodinger equation. Today we're going to be focusing on the persistence of regularity element of well-posedness, having already shown the local existence, uniqueness of solutions, and their continuous dependence on data in the previous two videos. So you know it by now, but this is the nonlinear Schrodinger equation, which we're studying, and there's no last-minute surprises. We're still taking s larger than n over 2 and p to be an odd integer. So I'm just going to quickly summarize what we've done so far, what we know from the previous two videos. And this is basically just so we have everything in a nice form for what we're going to need today in this video. So this is a long, horrible box of theorem, but don't be scared, it's nothing too complicated. So all it says is that for S, P, satisfying the usual conditions, any initial time t0, any initial data u0 in HS, we have a unique, maximal, strong solution in C0t HS to our nonlinear Schrodinger equation. So to be very precise, in particular about what does this maximal mean, whenever our initial data in HS has norm at most m, there exist maximal times t plus and t minus, which are at least as large as this function of the size of the initial data. So when the initial data is very small, this will be very large, and you know that this solution exists for a long time. And a unique solution u on some interval around the time t0 into HS, solving the nonlinear Schrodinger equation strongly, and that's all that this equation means. Just quickly, what did I really mean when I said maximal here? So this just means that if ever t plus and t minus were larger, these conclusions that I just said wouldn't hold. So i.e. Wouldn't hold for any larger t plus, we'll say t plus primed or t minus primed. And moreover, this last point, and I didn't actually prove this, it was actually the exercise from the end of the previous video, and I'm just going to pretend that you did it and you know it, because it's just a nice way to conclude the theorem. So moreover, if this endpoint time t plus is finite, and we only exist for a finite time in the forward direction, then we know that as we approach this endpoint of the interval, it should be t0 plus t plus, sorry, the norm of the solution blows up in HS. And obviously we have something similar at the endpoint in the negative direction. Okay, so that was a very quick explanation, because I've already spent a lot of time going over this in the previous two videos. So that's enough dwelling on the past, and it's time for us to look to the future, and in particular to the persistence of regularity. So this is the following. We're going to prove that with the same assumptions as for the previous theorem. If we further assume that u0 is now not only in HS, but in some HS1, with S1 larger than S, then in fact the solution u belongs to C of t0 minus t minus, t0 plus t plus, so that maximal interval of existence in HS, into HS1. So if the initial data additionally is in HS1, the solution will stay in HS1 for as long as it exists just in HS. So this is actually, I don't know, as I said, I think it's quite sort of surprising. So why on earth should we expect something like this to be true? Well, to understand this, we should really go back to the proof we did of local existence in HS. So how did we show this? We showed that this solution map, phi, and I'm just going to put a phi of t0 actually, just to emphasize that this has got initial data t0, because we're going to be using this solution map at lots of different times in the proof of our theorem. So we showed that this map was a contraction on this ball, which was the set of functions u continuous on an interval into HS whose norm in HS was always bounded by 2m. And this interval was of width Tm, where Tm is this constant, which is decaying in M, with some dependence on N, S, and P that doesn't really matter because those constants are fixed in this theorem. How did we prove that this map was a contraction on this ball? Well, we showed the following bounds. So we showed the norm of phi of u on C0T HS was bounded by the norm of the data plus some constant, again depending on fixed parameters, times the variable t, times the norm of u in L infinity of time and space to the power of p minus 1 times the norm of u in C0T HSX. Now this might seem a bit strange because actually when we proved the local existence theorem, we didn't really use this L infinity space. We just used the embedding of HS into L infinity because we're working with S larger than n over 2 to instantly bound this by the C0T HS norm and do our argument to show that this implied that phi mapped some ball to itself. But for us, in this part of the argument for persistence of regularity, it's actually really important that we only needed this bound in L infinity here. The other thing we used was this bound on the difference, and this is actually not going to be so important to us today. And the reason is because here we had these HS bounds, and these ones are unavoidably HS. We couldn't have put them into L infinity because of the way if you look back at the sort of Sobolev product estimate we were doing, and you try and put these ones into L infinity, you couldn't, because you'd sometimes need this one to land in L infinity and one of these ones to land in HS instead. It wouldn't work. Okay, so this was enough to show us that we had a contraction map on this ball. So if we think back to when we first proved the Picard iteration theorem in our, first or second analysis course, this meant that we could actually construct that fixed point as the limit of iterates of the map phi. So we could choose some initial point u0 in that ball. So let's call this st minus t0 u0, the free evolution of the initial data. And then the later iterates uj are just going to be that phi times u0 applied to the previous uj. So u1 is phi of u0 and so on. And we showed then that these converge on C0Tm HSX to the solution u, which is the fixed point and the solution of our equation. So it's just a small thing to note. You should be sure that this point actually lies in that ball B2M Tm, because otherwise the iterates won't necessarily lie in the ball, and there's no reason for those to be the ones that converge to the solution. We only know that the iterates converge when we start in the ball. Okay, so that's what we did. We're still looking to the past now, I suppose, showing the convergence in HS. We want to do better. We want to show these converge in HS1. So obviously, if our initial data U0 is in HS1, then we can see that our first iterate will still lie in HS1, or indeed C0T HS1. And in fact, we're going to show that maybe not on this interval of T0 minus Tm, T0 plus Tm, but maybe on some smaller interval, on some subset of this, these same iterates will converge to the solution U, but now in HS1x. Or, okay, actually, as I said, I put these converge in whatever those apostrophe things are called, because we're not actually going to get convergence in C0 to HS1, we're going to get some kind of weak convergence. But yeah, we'll get this solution to converge on some smaller interval in HS1. And the size of this interval might depend on the size of the data in HS, but it does not depend on the size of the data in HS1. U0, sorry. Okay, so maybe just to be clear, when I say that the sequence converges in HS1, I guess I really mean that we'll be able to show that the solution lies in HS1 on this extra, smaller interval whose size depends only on the HS norm of U0, not the HS1 norm. So why is this good enough? Why is that all we want? Well, if we look at our pretty solution up here, defined on its maximal interval, t0 minus t minus, t0 plus t plus, even if we knew that our data at time t0 lay in HS1, if we were only able to then extend it in HS1 by some amount of time depending on that HS1 norm, then since we have no control on the size of the solution in HS1, we couldn't guarantee we could carry on doing this for a long enough time. So we might start in HS1 and be able to extend it there for some time depending on the size in HS1. But maybe by the time we've reached this endpoint, we've grown in HS1, so we can only extend it for a shorter time now. And then we might have grown some more, so we can only extend it for a shorter time in HS1, and so on. And we might bunch up and reach some endpoint and never cover the whole interval that we want to. But since we already know our solution is continuous into HS, by working on a compact interval, we can control the size of the solution in HS. So maybe we work on some interval t0 minus capital T0, T0 plus capital T1. Then, by continuity of the solution into HS, we know that the solution has bounded HS norm on that interval, say by some capital M. So then, if we start at time t0 in HS1, we can extend our solution now in HS1 by some time, which depends on the HS norm of the data. This is what we said we're going to show. And the HS norm of the data is bounded by M. So then when we get to the endpoint, we know that the solution now is still bounded by M, because we're still on that compact interval. So we can extend by the same amount of time. Now the solution is still of size at most n, so we can extend by the same amount of time, and so on. So then we only have to do this finitely many times before we cover the whole interval. And this shows then that the solution is in HS1 on the whole interval that we looked at. And then since we can cover the whole open interval by compact intervals, this shows that the solution will be in HS1. So then the question is, why should we be able to extend the solution for amount of time in HS1, which only depends on the HS norm of the data? And this is because of this L infinity x, which is appearing in this inequality. And the point here is that we can do this whole inequality again with the S replaced with S1, and everything would be exactly the same. But then this time, for us to show that phi was a contraction map as before, we still need this thing to be less than or equal to half. That's what we needed to do. Last time we had to choose t sufficiently small, depending on this norm, to make this prefactor less than or equal to half. And because this norm is controlled by the HS norm, we could just do this by taking t sufficiently small, depending on the size of the solution in HS. Now we're working in S1, we don't want to have to take t sufficiently small depending on S1, but we don't need to, because we still have just this L infinity norm. It's still controlled by HS, because S hasn't stopped being larger than n/2, so we still only need to take t small enough depending on the HS norm of the solution. So this is, I know, a bit confusing and a bit fast, so let's try and now make this rigorous, do it properly, and write it all down. So it's time to prove properly this persistence of regularity. So I'm only actually going to prove that U is continuous into HS1 on the forward interval of existence, because as you can imagine, the argument in the backwards direction is just exactly the same. I'm also just going to prove that it's continuous into HS1 on compact subintervals of the forward interval of existence, because then you can just take a compact exhaustion of this full interval and see that the solution is indeed continuous on the whole interval. Okay, so let's consider any compact subinterval of that. T0 plus T plus, so let's say T0 plus T1. By the blow-up criterion in HS1, we know that it's in fact sufficient to prove, RTP remains to prove, that U is in L infinity of this compact interval into HS1, because this means that the norm of u can't blow up in HS1 on the interval, and we saw that whenever we reach the endpoint of the interval existence in HS1, then the solution has to blow up, so this can't happen on the interval I bar, so it must stay in HS1 on the whole interval. Here I'm implicitly using that u is locally in HS1 on some interval of t0, just because our initial data u of t0 we're assuming to lie in HS1, so by local existence theory in HS1 there's a local solution around time t0. Okay, so we said we want to use the control we have of u in HS, so let's let m denote the supremum over this interval I bar of the norm of u in HS, and we know this is finite because the interval is compact. Now we're going to split the interval I bar into n essentially disjoint subintervals, perhaps they overlap a bit at the endpoints, to write I bar as the disjoint union from I equals 0 to capital M minus 1 of intervals I. And just to be clear, I'm going to denote each I as Ti plus 1. So I0 starts at the initial time t0. And I do these in a certain way. So I want the length of each interval I to be at most this. So the minimum of Tm, so the time interval on which I can construct a solution in HS by Picard iteration, since the solution is bounded by m in HS, and some mysterious constant Cn S1 P star, which I'm not going to find right now, but it will appear later. But it's a constant, so it is something fixed depending on those parameters, times m to the minus p minus 1. And this I'm just going to call delta m, because apart from the fixed parameters n, s, s1, and p, it only depends on m. And we can do this with n less than or equal to the length of I bar divided by delta m. Okay, probably delta m doesn't exactly divide I bar, so we need to take the ceiling function. So we have a compact interval up to t0 plus capital T0. We split it into n subintervals, all of width delta m, and maybe one of them is a bit smaller than width delta m, and that's why we have this ceiling function. Now, since the width of all these intervals was at most Tm, and we know that the norm of the solution is bounded by m on all the intervals, we in fact have that the iterates uij converge to u in Cii HS, where uij are the iterates with starting points tj. So ui0 is s of t minus ti u of ti, which you can check lies in B2M II, and uji is then going to be phi of uij minus 1 starting at time ti. So at each time ti, we look at the interval ti plus 1, this is ii. We take the initial data u ti and have the corresponding iterates for the solution there, which will converge to the solution u in CHS on the interval II. But we want convergence in HS1, and we can do this by getting a uniform bound on the HS1 norm of these iterates on the interval II. So we can bound uij in CII HS1. I'm really sorry for all of the indices going over here. So you can bound this by the norm of u at time ti, which is our sort of initial time now, in HS1, plus some constant depending on n, s1, and p, multiplied by the width of the interval, the norm of uj minus 1 I in L infinity II L infinity x to the power p minus 1 times the norm of uj minus 1 I in CII HS1. Now this is a lot, but this is actually just exactly the inequality that I was discussing before that we showed in the local existence proof to show that phi matched the ball to itself. And I've used here so that uji is phi of uj minus 1I, which is why we've got uj minus 1s appearing on the right hand side and uj on the left hand side. So then to bound this, as I said, we use the embedding of hs into L infinity. So this initial data part stays the same. We have some new constant which is going to depend now also on s, because we're going to use the embedding of hs. Call it CNS1SP star. So this is the constant that was used to define the width of the II, multiplied by the width of I, the norm of u, j minus 1, I on L infinity into hsx, not hs1, happy nice 1, times u, j minus 1, I, and cii into hs1. Okay. We know that the norm of u on all of these intervals II is bounded by m. So this term is at most m to the p minus 1. So then by our first condition, or actually second condition, on the widths of I, we have that this is going to be bounded by a half, because we chose I small enough. Okay, actually we didn't choose I small enough, because we should have put a half in front here. Sorry. Okay, so then once you know this, by induction, it follows that the norm of uij in CII HS1 is less than or equal to twice the norm of u at time ti in HS1. So I mean, this is really easy to check by induction from this inequality above. Okay. So in particular, we have that on each of these intervals, II, at any time in the interval, maybe I should get another colour for this, there's a lot of scribbling already. The sequence uij at t, so one of these iterates, uj on the interval I, at the time t, is bounded in HS1 by twice the norm of u at ti in HS1. Okay, if we already know that u lies in HS1 at time ti. So this means in particular that it has a weakly converging subsequence. So we can find subsequence jk, say, so that ujki at time t, for any t in ii, converges weakly to u at, some function v, depending on I of t, say. And this is weak convergence in HS1. But in fact, weak convergence in HS1 controls weak convergence in HS. So this also converges in HS. And we already know that these iterates uji converge strongly to u in HS at a fixed time t. So in fact, we must have that vi of t equals u of t. And since all of these iterates at time t had norm at most twice the norm at time ti, we get that the norm of u at time t in HS1 is less than or equal to twice the norm of u at time ti in HS1. Okay, so in particular, since ti plus 1 is in the interval ii, we can apply this at time ti plus 1 to see that the norm, by the time you reach the end of the interval ii, in hs1 has at most doubled. Okay, we have that the norm of u at time ti plus 1 is less than or equal to or twice the norm of u at time ti. So then by induction, we have that the norm of u at any time ti, if we start from time t0, is less than or equal to 2 to the power of I times the norm at u t0. Since we assume that our data lies in hs1, so u t0 is in hs1, this is finite. So this actually shows that u lies in hs1 at all of these times ti, which then shows from this that it lies in hs1 on all of the intervals ii. And so even better, the number of intervals I was bounded by n, capital N, and that capital N, if you go back up and check, depended only on the width of I and capital M, so the size of the solution in HS. So we have some uniform bound on the HS1 norm of the solution over the whole compact interval T0 plus T1 by something which depends only on the initial norm in HS1 and the HS norm of the solution over the interval I, or I bar. Okay, so sorry, I think these words are unnecessary here. No, it's a bit messy, sorry. So yeah, indeed we've shown that the solution is bounded in HS1 over the whole interval I bar, depending in this nice way on only the norm of the initial data and the solution in HS, which completes the proof. We've shown that the solution is bounded in HS1, it can't blow up, hence it must continue to exist on this whole compact interval. The compact interval is arbitrary on the maximal time of existence, or at least in the forwards direction, so we must continue to exist on the whole forward time of existence. Okay, great. So just lastly, before you go, this time the exercise is quite a lot more than the previous two videos, and it's actually the exercise that was originally intended to be done for the class corresponding to the course, corresponding to the video, and it's to do everything we've just done, the existence, uniqueness, everything, but for the nonlinear wave equation instead of the Schrodinger equation. So it's pretty much all the steps are exactly the same. The only thing that changes is obviously the equation. We now have, well, okay, it's not the only thing that changes. The key thing that changes is the equation. We now have the wave operator, the time inversion operator. And I suppose the key thing that changes in the proof is that we now have initial data in terms of not only the function, but also its time derivative, which will lie in hs minus 1. And because we have this s minus 1 appearing, we now need to take s larger than n over 2 plus 1. So the difficulty is that to be able to do all these kind of iterative arguments to get uniqueness and persistence of regularity, you now need to not only control u, but you need to control its time derivative, because you don't want the norm to get too big and so on, most of the arguments we do. So you need the norm of the time derivative of u also not to get large, so you need to work in a space which controls both u and dtu. Okay, yeah, I hope this was helpful, and thank you for listening.